Hi everybody. I'm gonna make this little supplementary video to go through the proof of why wave packets move at the group velocity and not the phase velocity. Now this proof is kind of involved, and I think it's somewhat secondary to what we're doing. I wouldn't expect you to reproduce this uh, on an exam or on homework, but it is worth seeing this once in one's life. So I'm going to go through this for anybody who's interested. By the way, I'm going to be testing out here a different recording setup, one that Colleen Countryman, who is awesome in all things technology related and in many, many other ways as well, what she suggests. So we're just going to give this a try. Okay, so in case it's not clear, I'm essentially using a camera as a dock cam, and then you can still see me talking to you on the lower right. Okay, so wave packets and the group velocity v sub g. Okay, so what we need to remember is that a wave packet is the let's see, uh, is given by a continuous sum over different plane waves. So I'll write that as an integral. We've got this sort of envelope function a of k. So this a of k, right, tells us how much of each wave number is contributing to the wave packet. And we have this a of k e, and we've got a plane wave e to the I kx, k times x, minus omega, and I'm going to write this as omega sub k t dk. And the reason I'm writing omega sub k is to remind us that omega is going to be different for each wave number. Remember, each plane wave has to satisfies uh, h bar squared k squared over 2m equals h bar omega, right? So every time we have a different k, there's also a different omega associated with that. So that's why omega is k dependent. So what does it? What does this look like, right? So what we're gonna typically have, and what you saw in the FET, right, was an A of k that generally had some sort of Gaussian-like shape, that sort of bell curve shape. We're gonna work this derivation out, assuming a fairly narrow A of k. So let's draw that here. So I'll plot that here. So if we have k and then a of k, I'm going to assume that it's fairly narrow and is peaked about some sort of central wave number, which I'm going to call k sub 0. Remember, this is not the shape of the wave packet. It's just, right, because the wave packet we see as a function of x. This is just showing us what wave numbers contribute in the integral. Okay, so how do we prove that a wave packet really does move at the group velocity? I think it helps to first draw a picture. So what we really care about is not the wave function itself directly, but everything physical is going to ultimately come from the probability density psi modulus squared, as we've seen in the last couple of classes. So let's think about what might happen if we had a moving wave packet. So let me first draw the wave packet as a function of x. And let me do this at t equals 0, label that. And so I'll draw psi of x t modulus squared. That's our probability density. And let's assume that there's a shape here. At t equals 0, my wave packet looks something like this. I'm going to assume it's sort of bell curve shaped again, but it's not the same as that. So we'll now look later at t equals t. And if I, again, draw a graph here, plot x versus probability density, and let's assume that this wave packet has, in fact, moved to the right. So we now get a shape that looks something like this. If this wave packet really is moving to the right at x equals at v equals v group, so let me just pick a particular point here. So let's assume that this peak of the wave packet is at x equals x naught, right? What we want is that, well, that should be at 0, sorry, t equals 0. What we want, right, is that, right, so here's the same point, x naught over here. We want the probability density at x naught at this time t to be equal to the probability density sort of further back at t equals 0. And in particular, I think you can convince yourself that we want this to be sort of, if the wave packet is moving, right, so it'll go a distance v group times t here. So this, we want this to be x naught minus v group times t if wave packet moving with the subgroup. If this were the case, that would correspond to a wave packet moving at the group velocity. Is this doing some funny thing with the camera dock-cam focus? I can't tell. I think it might be. Yeah, it looks a little, sorry, it looks a little fuzzy here. I can back this up just a little bit. Whoops. See if that helped things at all. Does that maybe help? I'm not sure if it does. Okay, so so anyway, let me just carry on. Let me carry on here. So what we want to show is the following. So we want to show that the same thing holds for all values of x, not just the special point x naught. We want to show that psi of x t modulus squared is equal to the wave function psi x minus v group times t at t equals 0. Okay. So this is the goal of the argument, of the somewhat lengthy argument we're going to dive into. Okay. So the argument starts really by start with a wave packet. And so we want to start with this expression up here. And so what we but I'm not going to just recopy that. But then what we're going to do is we're going to tailor, we want to put in somehow this omega as a function of k here, right? Because we know that there is a k dependence, but it's right now implicit. So assume uh, that assume narrow wave packet and that sort of in the range that that matters, right? That if this interval only has support over a fairly narrow range of wave numbers, uh, so we can Taylor approximate. So omega, so the dispersion relation, so that omega of k is approximately equal to some uh, omega naught, and so this is going to be the angular frequency at k naught. Okay, let me just note this omega um, plus d omega dk evaluated at k naught times k minus k naught. So this is the first order Taylor expansion. We're going to assume that higher order terms are negligible, or that equivalently that higher order terms that would involve um, larger k minus k naught squared. If this is a sufficiently narrow spread of uh, spread in k, then the interval is not going to have support. This interval won't have support for large deviations, for large k sort of significantly different from k naught, and can get away with this. And then if we plug this in here, if we plug this in, and that we can sort of do a little bit of algebra. So do algebra. So in particular, right? So this our kx minus omega sub k t becomes kx minus omega naught t uh, plus, I forgot one step. I was going to actually call this my group velocity, because that is our group velocity, k minus k naught. Sorry about that. So we have my kx minus my omega naught t, and then I have this term, so I have minus v group k minus k naught times t. Okay, so here's where the algebra gets a little bit messy. What we're going to do next is to sort of manipulate this a little bit. I'm going to add a term, k naught x. I can do that as long as I subtract the same term, minus omega naught t, um, minus vg k minus k naught t. I'm going to sort of do this in order to kind of rearrange some stuff. This is ultimately going to go in this exponential up here, and I'm going to try to pull out or separate out any stuff that doesn't depend explicitly on k, so that it can be pulled out of the integral. So if I do that, right, this term doesn't depend on k, nor does this term. So that's going to leave me with a k naught x minus an omega naught t Okay, so I've got now the rest of these terms. So I have plus kx minus k naught x minus vg k minus k naught t. But hey, I can factor this, right? I can pull out k naught x minus omega naught t. I can pull out a factor of k out of both of these terms here, so I have a plus k. So I have plus k or minus k naught times x minus vg k minus k naught t. Factor one more time, I can pull out the common factor of k minus k naught, and then this becomes minus omega naught t plus k minus k naught times x minus v group times t. Okay, so far this seems like a bunch of algebra, and I know the motivation for it doesn't seem particularly lucid, but hang on in there. Okay, so I'm going to advance the page. Okay, well yeah, so now what we're going to do is we're going to plug this back up here. So, right, our psi of xt is going to be equal to minus infinity to infinity. I have my sort of weighting function a of k. And now I'm going to write exp rather than e so that I don't have too many tiny subscripts. So I'm going to have exp I, and then I have kx minus omega k t, which is going to be, now this entire thing, k naught x minus omega naught t plus k minus k naught x minus v group t, yes. And I'm going to close the parentheses, and we're integrating dk. Now, as I promised, I'm going to pull this piece of the exponential, which doesn't depend on k, out of my integral. So if I do that, and then so now I'll just go back to e to the x. I'll have e to the I k naught x minus omega naught t out there. And then I have my integral again, k e to the I k minus k naught x minus vg t dk. Okay, so here's the thing. So this ostensibly holds at all at all values of t. But right, if this holds at all t, this should also hold at t equals 0. So consider what happens at t equals 0. Well, just plugging in 0, we get psi of x 0. So every term with a t vanishes. So we have now e to the I k naught x. So that e to the minus I omega naught t goes to 1. We have my integral again. I have my a of k. Now I just have e to the I k minus k naught x dk. Okay. So this is now right, it's supposed to hold for all x. But we can go ahead and, since this holds for all x, we can go ahead and since this holds for all x, we can go ahead, evaluate at x minus vgt. And we're allowed to do this. We're essentially sort of shoving symbols around. If it makes you feel better, I could sort of just like prime all the x's in this equation, but I'm just going to go ahead and do it. So everywhere I see an x here, I'm going to substitute x minus vgt. So this gives me psi of x minus, what's x minus v, let's redo that, psi of x minus vgt 0 equals e to the I k naught x minus vgt integral a of k e to the I k minus k naught x minus vgt dk. Okay. So now let's look at these two expressions, right? Our wave function at t equals 0 and further back, and our wave function psi of x t. Notice that the actual intervals are exactly the same. The only thing that's different is sort of these phase factors in front. So in particular, notice, so let me just star these, because these are the two equations we really need to look at. So star and we double star this and star this. Notice comparing star and double star that, like that, now psi of x t and psi of x minus vg t 0 differ only by factors. So let's see what we have to do, right? So to get this back, I need to, from this, I have to multiply by e to the minus I omega naught t. And I've got to cancel out the e to the I k naught minus to the minus I k naught vgt. So I'll multiply by e to the I k naught vgt psi of x minus vgt 0. And if we plug this in here, we will recover exactly that. Well, we're nearly done, because now if we just take the modulus squared of both sides, so psi of xt modulus squared, when we modulus square all of this, right, all of these complex exponential terms are just going to go to 1, right? Because we're going to multiply by e to the I omega naught t and e to the minus I k naught vgt. So we're just going to end up with psi of x minus vgt 0 modulus squared. Well, that is exactly what we said we wanted to show. And so we're done, and that completes the proof. Okay, so a somewhat lengthy argument, but hopefully this has convinced you that it's plausible that a wave packet moves at the group velocity.